Thanks for being here, everybody. Today we are joined by Christopher Goes, who is the research and development lead at Heliax and co-founder of the Anoma project. He also wrote the first Zcash block explorer back in the day and was recently a speaker at ZCon 3 in Las Vegas. Today, he'll be spending some time with us at the Zcash Foundation to give us a high-level presentation on Cosmos, IBC, and the Tendermint stack in general. This call is being recorded and it will be posted to the ZF YouTube and shared across our socials going forward. So with that said, we'll get this going and I'll toss it over to you, Chris.
Thank you. Thanks for the intro. So my hope is to do this call as a kind of collaborative, I'll lead, but a collaborative whiteboarding session. And I had a conversation with Jack prior to this over kind of what I should focus on. And I've adopted as my goal to kind of see if I can help the Zcash community map out some of the options around proof of stake. Because it seems like, I was there for Nathan's talk at ZCon 3. It seems like there are a lot of options, and the Zcash community has some sort of requirements or maybe things that you guys want, as I understand it, at least, out of a proof of stake system. And then there are a lot of possible proof of stake systems out in the world. And it seems like in order to get from those requirements to a decision about a specific one, it would be helpful to understand which components of the design are coupled and which are sort of orthogonal. And also in evaluating an existing stack like the Cosmos stack, I think it might be helpful to understand sort of the architecture of where certain components sit, and do you have to take them all at once, or can you take the little bits that you want and only those bits? So my objective in this call is going to be to try to help with that. But in order to help with that, I need feedback, because I don't, to me, the Zcash community is this magical amorphous entity which produces a blockchain Zcash and uses it and produces privacy and does all of these wonderful things, but it's hard for me to, it's not a person who I could talk to, right? So I would appreciate from you guys as well, please stop me, please ask questions, please, if there's some, especially, engineers or from a high level, really anyone, if there are parts of this that don't make sense, or if I don't seem to be going in a direction that's most useful to you, let me know, and I'm happy to change course. I have, I think, enough of a broad understanding of Cosmos and the IBC stack and proof of stake to kind of go anywhere you want, at least at a moderate level of detail. Of course, if you want really specific details over, how Penumbra's proof of stake system works or something, then you should go there. The most I could do is explain kind of the architectural trade-offs of some of these different design choices. I'm going to share my screen here, which is a whiteboard, and let me know if you can see this. Can you see it?
Yes.
Keep in mind that when I see this screen share, I cannot see you anymore. I think I can't easily fix this, so okay. Someone has to say something. I can't see the hands raised.
Sure.
Thanks. Okay. Yeah. To just provide a little bit.
Could you, real quick, Chris? Could you zoom in just a little bit for the?
Absolutely. Let's see. I think I can do this. Is that better?
Yes. Thank you.
Cool. Yeah, so just as a little bit of additional context, I early on, around the time of Zcash launch, I was trying to learn about different blockchains at the time, and Zcash had really interesting cryptography, and I was looking for a way I could contribute, and I don't think there was any block explorer, actually. So just right before Zcash launched, I wrote for fun. It was called Zchain because it was a cute domain name, which was one of the first Zcash block explorers at explorer.zcha.in. I ran it, paid for the servers for a few months, and then I think I handed it off to some Zcash miner, Flypool, I don't remember actually, to operate for a long term. And as far as I know, they continue to, although they added some annoying ads. I don't know why they did that, but the block explorer design is still mostly unchanged. So if you don't like it, it's still my fault. Okay, that's my original affiliation with Zcash. Since then I worked on the Cosmos project, particularly the IBC protocol. Now I work on Anoma and Namada. Mostly today I'm going to go over the kind of design options that are relevant for Zcash, as I understand what Zcash is looking for in proof of stake. I think it might make sense to start. So this is what I discussed with Jack. I think it might make sense to start with a high-level overview of what the Cosmos stack is and what it consists of, because even if you don't want to use the particular components of the Cosmos stack for Zcash, or even if you only want to use some of them in a potential proof of stake upgrade. The Cosmos stack at least does many things that a proof of stake chain must do. So Zcash will need to do them somehow. So even if you don't want these specific components, I think it's architecturally a helpful way to think about things. So I want to like diagram out the stack. After I do that, I want to go through some of the implications. I understand the Zcash community has a lot of requirements or maybe considerations in considering proof of stake. Jack sort of listed three, which are here, and I'll try and go through, as I understand them, what these different design options would entail for those maybe requirements or preferences that the Zcash community might have. And then I wanted to, at the end, just give kind of like a layout of, Cosmos, even Cosmos proof of stake is not one thing, it's many things. There's several different options within that broad umbrella, and I wanted to kind of explain what they are and how they relate to each other and which ones are kind of the same and which ones are like fundamentally different in ways that might matter for Zcash's considerations. Does that all sound good?
Perfect.
Okay, please interrupt with questions. Okay, so let's start with number one, high-level overview. Just tell me anytime if I need to zoom in more. Okay, so Zcash, as far as I understand, architecturally is still kind of in the Bitcoin world. And in the Bitcoin world, everything is sort of architecturally intermingled. There's consensus, there are transaction validation rules, or what you might call a state machine, there are peer-to-peer network rules, and they're all like melded. At least in the Bitcoin database. When I read it, they were. Perhaps, I don't know all of the details of how I guess Zebra and the ECC Zcash client implementation are architected, but if they're still similar to Bitcoin in this aspect, then there's kind of a melding of these, all of these functions. And I suspect that Bitcoin did it originally because Bitcoin's consensus is pretty simple, and Bitcoin's transaction validation rules are pretty simple, and Bitcoin's peer-to-peer rules are pretty simple, and many of them, it's just like it's straightforward to implement it that way. Bitcoin wasn't aiming to be abstract; it was aiming to do one thing, and that made sense. But in a sort of more, in a world which is more complex, and especially in a world like the Cosmos world, which aims to be modular, it makes sense to split these apart. So in the Cosmos world, and also to some extent in like Polkadot is also pretty similar in this aspect, even. In some ways, Ethereum is moving in this direction. In the Cosmos world, there are separate components which have sort of specific interfaces. And there are like large groups and then sort of small groups. And the large separation is between consensus and the state machine. So, for example, if you've heard the name Tendermint, Tendermint is a consensus algorithm. And consensus means that Tendermint is responsible for coming to agreement on an ordering of blocks. That's it. So you could have Tendermint as a BFT consensus algorithm, which means that you need to choose a particular set of validators to operate it for any particular block, and they need to have public keys, and a 2/3 quorum of those validators is sufficient to produce a block. But you could also have, Bitcoin has what could be termed Nakamoto consensus. And in Nakamoto consensus, the canonical chain or the ordering of blocks is just chosen based on which chain has the most cumulative work. So you can, this separation is not dependent on BFT or proof of stake. This is just a separation into the constituent components of kind of a distributed database system like blockchain. So Tendermint as a consensus system is responsible only for agreeing on orderings of blocks. It is not responsible for the semantics of transactions. So there's kind of like two Tendermint in this kind of architecture. Transactions are opaque data blobs. The application state machine determines what they mean, or so to speak. Tendermint just says like, I can take maximum 2 megabytes of transactions in a block or whatever, here, send your bytes here. And the state machine is responsible for determining how they actually get applied to the state. So state machine interprets transactions. And between those two, in the Cosmos world, there's an interface known as ABCI. ABCI stands for the Application Blockchain Interface, I think. And IBCI is responsible for communications between Tendermint and the state machine. So this arrow is basically unidirectional because Tendermint is the driver in the way the Cosmos stack works. So Tendermint makes calls to the state machine. Tendermint accepts transactions over the peer-to-peer system. It sends those transactions to the state machine. The state machine executes them and is responsible at the end of each block for giving Tendermint an updated state root, which is like the root hash of the Merkle tree of each block. And Tendermint then can broadcast this so that everyone can see the validators read on it. So this separation, it's important to, I guess, note that this separation says nothing about what consensus can be or what the state machine does. So the separation holds for it's like based on the architecture of distributed systems, if you will. So the separation holds for private blockchain, like using cryptography blockchains like Zcash, for transparent blockchains. We can agree that they are bad, but they can still use the same separation, if that makes sense. And this separation is important to understand in thinking about how to use the Cosmos stack because it affects which choices are coupled. So Cosmos, for example, offers Tendermint as a consensus algorithm. And Tendermint is a pretty unified thing. It's not easily split apart. So if the Zcash community wanted to adopt Tendermint as a consensus algorithm, you kind of need to take the whole thing. I mean, if you're willing to spend a lot of time and a lot of Go engineering effort, of course, you can modify it, but it's not designed to be modular as it is. So if you take Tendermint, you take Tendermint peer-to-peer and Tendermint consensus, but that does not in any way restrict the state machine. Yeah, and I guess the other part, I want to get to number 2 and the implications here, but the other part here I want to explain is IBC. IBC, so in the sort of Cosmos lexicon, maybe just to help map, consensus is Tendermint. The state machine Cosmos offers something called the Cosmos SDK to write state machines in, and then the Cosmos sort of stack also offers a protocol called IBC, which is designed for interoperability between blockchains with well-defined light client algorithms. I think that's the best way to put it. So IBC is not specific to Tendermint. This is important to note, at least architecturally. IBC is supported at the moment. It's supported by Tendermint very well. It's supported to some degree by Polkadot's relay chain consensus algorithm, which I think is called Babe. There is a Solidity implementation that works. It's just kind of slow. So some people are working on some zero-knowledge rollup based Ethereum IBC adapters instead. And there are many separate bridges, that talk to IBC compatible blockchains, but are not IBC themselves. So IBC is a protocol, which means that it's not a specific software implementation. There are 2 implementations of IBC that are kind of considered production ready. One of them is in Go, the other one is in Rust. Both of those are developed by kind of people in the Cosmos ecosystem. But it's important to note that these 3 choices are separable, as in, at least in principle, Zcash can pick amongst any of them without being constrained into the others. Now, they work well together. I mean, like Tendermint, the Cosmos SDK in particular is built on top of ABCI. So it would be very difficult to use the Cosmos SDK without using Tendermint. I guess that's the one hard dependency. I should revise slightly. But it's completely possible to use Tendermint without using the SDK. It's possible to use Tendermint and IBC with or without using the SDK, and it's even possible to use only IBC. That might entail slightly more work, like writing a light client algorithm if Zcash decides to craft a new sort of novel BFT consensus algorithm that doesn't yet have a light client, but it's still possible. And IBC is very carefully designed not to be Tendermint specific. So it would be, you wouldn't need to change IBC. You just need to add a little component for the new light client algorithm, or so to speak. So I think that it's helpful to start with this distinction because it allows us to answer already definitively one implication. So IBC compliance does not place constraints on the state machine. IBC compliance is something at the edge of the state machine. You could think of this like a computer. So a computer which supports TCP/IP. Supporting TCP/IP places constraints on the edge, or so to speak, of the computer. Like it means that you need to have a network card which speaks TCP/IP, or you need to have a software implementation which implements the TCP/IP protocol stack. But it places absolutely 0 constraints at all on what the computer does internally. So internally, your computer can use cryptography or no cryptography, or it can take input from Cosmic microwave background radiation and use that as randomness, or it can use a continuous string of ones as randomness. It could do anything, right? TCP/IP is only constrained on the edge of the system. It's not a constraint on any of the other interior operations. So in this analogy, Zcash is like a computer, a distributed replicated state machine. Can't have randomness, but otherwise, IBC compliance does not place constraints on what the Zcash state machine could do at all. It's, of course, the Zcash state machine implements private transactions using zero-knowledge proofs, and many IBC compatible blockchains don't support any form of privacy at all. So they will not, IBC itself is kind of not opinionated as to whether the transactions or cross-chain messages flowing over it are private or not. That has to do with what those messages contain. So other chains won't magically become like Zcash just by virtue of Zcash supporting IBC, but Zcash itself is not constrained by it. The same applies, at least with regards to the specific phrasing of this question, the same applies to Tendermint. So Tendermint would place constraints on Zcash's consensus. So for example, if Zcash adopts Tendermint, Tendermint has limits in the number of validators that can be supported because it has n-squared message complexity. So in practice, Tendermint is limited at the moment to a few hundred validators. So that would be a constraint, perhaps, on Zcash. But Tendermint does not place constraints on the Zcash state machine. So stuff like cryptography, like programmability, like the issuance rules for Zcash, even the rules governing expiry for transactions, everything like this, everything that governs how a transaction is interpreted by the state machine, what the bytes in a transaction mean, or so to speak, all of those choices are orthogonal to both IBC and Tendermint. And even in a slightly more general sense, even if you were to consider a different consensus algorithm, they would also be orthogonal to that. So I hope that's maybe a helpful clarification on some of the choices here. Yeah, there's another distinction that's really worth noting is Cosmos is used as kind of a term to refer to a very broad collection of things. And in fact, those things are distinct choices that are available to Zcash. So Cosmos, can refer to a community, which is great, and I hope Zcash talks to that community. It can refer to the Cosmos SDK, which is a specific piece of software written in Go that can be used to implement state machines for blockchains. So, for example, if Zcash wanted to, you could use the Cosmos SDK to implement something like the Zcash state machine. Like you could try and use the Cosmos SDK to implement some sort of like bindings to Orchard. The Cosmos SDK includes a lot of things that Zcash might not want. Like it's kind of it's a framework, and that it includes different modules. And one of those modules is proof of stakes. There's a specific proof of stake system that's available in the Cosmos SDK as an implementation. There's also a governance module which uses coin holder governance, coin holder based voting. And I gather that this is something maybe that Zcash doesn't want, or at least that there's not a precedent for in existing implementations. That's an orthogonal choice. You can use the Cosmos SDK and not use that model, but a fair amount of the Cosmos SDK is the scaffolding, and then there are a lot of specific modules, and those choices are independent. Now, there are often projects or blockchains that are using the Cosmos stack, like in the Cosmos ecosystem, often make many of the same choices. So like many of the Cosmos Hub, for example, which is the first blockchain, uses Tendermint, uses the Cosmos SDK, and all of the Cosmos SDK's modules like governance and proof of stake and reward distribution, and it supports IBC. And many blockchains in the Cosmos ecosystem do the same thing, and then they add their own specific application thing. Like Evmos does all of that, and then it adds an EVM module. Or Osmosis does all of that, basically, and then it adds their DEX module, right? So that's a common route. However, it's not clear. I don't want to be super speculative here, but it's not clear to me that it's the route that would make most sense for Zcash, based on what kind of I understand of Zcash's preferences, in particular because it entails the Cosmos SDK has this whole transparent account system, and it's not clear to me that Zcash needs this because it's designed to provide coin functionality for transparent transfers to blockchains that don't have any kind of transfer functionality at all. And Zcash's state machine, as it exists, already has both shielded and transparent transfer functionality. So, it's not clear to me that, like, unless you want a second implementation of that, it's not clear to me that that would add too much. Similarly, it seems like Zcash probably doesn't need the governance module. Another consideration that might come into play is that, as I understand Zcash, most of Zcash's cryptography is implemented in Rust, and the ZF's client is implemented in Rust, and the Cosmos SDK is implemented in Go. And that is possible to bind, but it is like tricky. And so far, I've heard a lot of people saying that it's like easy in theory, and then I've seen absolutely zero people actually launching production systems which do it in practice. And that combination of data points makes me very suspicious. I haven't tried, but yeah, just like 2 cents. Yes. So, but for example, it would be possible for Zcash to use Tendermint and try and like bind Tendermint to the existing Zcash state machine, which is written in Rust. Now, this does mean that then Zcash would need to implement proof of stake. So then you could maybe, port from the Cosmos code, but you wouldn't be able to use the proof of stake module, which is in the Cosmos SDK, unless you use the Cosmos SDK itself. But that, compared to like the complexity of the entire Cosmos SDK or something, implementing only proof of stake is maybe not, not necessarily that difficult. Although I don't know, of course, your engineering capacity exactly or whatever. But you could easily, like, there are IBC modules written in Rust, so you could use Tendermint, the Rust implementation of IBC, which is compatible with Tendermint, the existing Zcash Rust state machine, and then maybe like, as far as I know, there are 2 implementations of serious proof of stake systems in Rust in the wild. There's the implementation that's part of Namada, which is a project that I work on. I can describe that implementation in detail if you're interested. And there's the implementation in Penumbra, the project Henry DeValence works on. Those implementations, it's worth noting, are both doing the thing which I just proposed for Zcash, as in they're both using Tendermint and IBC, but not the Cosmos SDK. I can't speak as to Henry's choices specifically. Our choices were based on the fact that we wanted to work in Rust, and that the Cosmos SDK is a large software dependency to add to your project. As in, if you don't want all of the things that it does, it's like more code surface area than you potentially need. So yeah, maybe some considerations there. Okay, yeah, I should stop here for questions actually on this sort of conceptual separation. Yes, please.
Go ahead, Alfredo.
Yeah, thank you for explaining that. So you separated the Cosmos world in 3 main areas. In Tendermint, you said, like, for example, where is the peer-to-peer in that? Is in Tendermint side?
Right. Good question. In the Cosmos stack, Tendermint does the peer-to-peer stuff. So Tendermint is responsible for gossiping transactions, and Tendermint or validators pick which transactions to include in a block. Those transactions are then sent to the state machine to be executed.
So also Tendermint does some of the consensus rules that are more abstract, like the block size of the number of transactions, stuff like that. And for example, we in Zcash right now, for example, only accept transactions which are of a specific version that's in the top of the transaction. We look for transaction to be B4 or B5. Will that be in the state machine or in Tendermint in this?
That would be in the state machine. So okay. Tendermint implements the validity rules, which are related to opaque transactions, like transactions as data blobs of bytes that have a length. And that's all the Tendermint implements. All of the rules related to interpreting the contents of transactions, like decoding them via some kind of deserialization and interpreting things like a version field or a expiry time or replay protection, those are the responsibility of the state machine.
So let me ask you the last one. What IBC is?
What IBC is?
Yes.
Right.
Like, can you put me an example of something Zcash do that will fit in the IBC category, or something Bitcoin do? Or
right. Also a good question. I'm not sure that anything Bitcoin or Zcash does fits in the IBC category. IBC is concerned only with interoperability. IBC does not implement any regular state machine features. It doesn't implement shielded or transparent transfers. IBC is concerned only with allowing different blockchains, which use different consensus instances, to send and receive messages.
Got it. Thank you, Chris.
Deirdre?
Yeah, thank you for the overview. One of the things that we will probably have to change no matter what is that the block header of Zcash blocks currently encodes a lot more information in it besides the proof of work solution, hashes of the blocks and all that sort of stuff. It includes, if you go back in the archaeology of Zcash, it has included commitments to several different kinds of things that are also in the data of the block, including like commitments to the current state of the no commitment tree of blah 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 blah. Do you see any problems with updating Zcash block headers to a proof of stake world when we have other stuff in there besides kind of classic, instead of proof of work solution, you have a quote proof of stake solution, or maybe nothing like that at all?
Right. Do I understand correctly that these values are primarily like additional computations performed by the miners because they're convenient or something like this?
Yes, they are things that have to be checked with by all the consensus validating nodes to make sure that when you're getting gossiped a new block, that everything that you're computing in all of the transactions contained in that block and the prior best chain that you are looking at comports with the commitment or whatever it is that is in that field in the block header.
Right. In principle, no, that seems fine.
Cool.
With Tendermint specifically, you'll want to take a look at the ABCI API. And in particular, I mean, Tendermint does have its own block header type. So at the moment with ABCI 1, the easiest way to kind of adapt these would be to have there be like one mandatory first transaction that always has to be in each block, which encodes the extra information or something. Or that, or if it's sufficient, you could also make the proposer compute something at the end of the block and then commit to it in the block header. That you can do with any interface modifications already.
That's great. Awesome. Thank you.
The other note I would add is that Tendermint, I'm not part of the Tendermint development team, so I don't want to make commitments on their behalf, but I think the Tendermint development team expects to ship ABCI 2 pretty soon, like in the next quarter or two, so probably amenable to Zcash's schedule. And ABCI 2 adds many additional configuration points for applications to directly control and check the contents of block proposals, as in you can deal with the block as a whole more than, in addition to individual transactions.
That's
so
great.
were you to want custom header fields or stuff like this, that's easy to implement.
I think that would work well with the current way we validate. At least in the Zebra way, we split up as much work as we can between a chain, a block, its transactions, the pieces of its transactions, and being able to kind of like parallelize as much as possible. And then at the final step, we check this block that we see versus our view of state, of the whole chain state. And then we say yes, no, and then we can plug that into the API and say yes, no, or throw it in the bin.
Right. Yeah, I think you can look already at the interface definitions for ABCI 2, and I believe there's a great presentation by Dave on YouTube somewhere. I could find a link after. I don't have it offhand, but yeah.
Cool.
Okay. Next, any other questions?
Nope. I think we're good to move on.
Okay. Next, I wanted to start tackling the first of these implications here and try and the first question here is, can individual users participate in consensus, or do they have to delegate to large validators? Here, I want to separate out the constraints of BFT consensus and of proof of stake. These are different things, and they apply different constraints. And Zcash can choose between them independently. So in navigating the constraints, it's important to understand which come from BFT consensus and which come from proof of stake. Cool. So I'm going to start with BFT consensus because it's kind of the root reason for all of these constraints, as will become clear. So BFT consensus, Tendermint, for example, is a BFT consensus algorithm. BFT consensus, I'll spare you the history. There's a great old paper by Leslie Lamport involving weird analogies. BFT consensus basically means that there are a bunch of public keys voting on blocks. And BFT consensus achieves, for a formal definition of consensus, which includes finality, safety, and liveness, BFT consensus achieves the theoretically best possible result, which is that you have safety and liveness under an assumption that less than a third of the actors by vote weights. And note here the distinction between vote weights and stake. So BFT consensus deals in vote weights, which is like a number that's assigned to a public key. And you can think of there as being maybe there are 100 different public keys that vote in consensus, and each of them is assigned a number from 1 to 5. And if you add, let's say the total is 250, then you need 2/3 of 250. Now I reveal that I can't do math. I don't know, 180 or something to commit a block, right? So how those numbers get assigned to the voters that's the proof of stake is the how in this relation. But BFT consensus only deals with public keys which have voting weights. And yeah, as a brief summary, basically what happens is that Tendermint is a two-phase algorithm. So proposer makes a proposal. They send that proposal up around to a bunch of other validators. They get what's called a pre-vote on it, and then they do another round called the pre-commit, which references the pre-vote. And the reason for 2 rounds is kind of technical, has to do with both maintaining both safety and liveness under the possibility of Byzantine adversaries. And there I will sort of refer you to the Tendermint paper. But it's important to note this is not a Tendermint specific restriction. So BFT consensus algorithms are all going to be subject to this less than 1/3 Byzantine constraint, because that's sort of theoretical. A good way to think about it is that if you have a pie and you divide it into two-thirds, or so to speak, then there's going to be a 1/3 overlap. And if you had more than a third Byzantine, then there would always be the more than 1/3 Byzantine could always agree with one half that the block was A and with the other half that the block was B. And that then you would have a safety violation because you would finalize 2 different blocks. So that's the reason for the theoretical bound. Yeah, I would dive into that with more diagrams, but I don't think it's that relevant to the Zcash specific question, so I'm just going to move on. But what I think is important to note here as it relates to the Zcash specific questions is that, as might be evident from my brief explanation, BFT consensus requires sending a lot of messages. So it's different than proof of work. So in proof of work consensus, one miner mines a block and they send it to people, and it's either part of the new longest chain or it's not. It's very asynchronous. From that perspective, it's great and simple and has easy to understand. There could be as many miners as you want, and the number of miners doesn't, eventually you end up with, I don't know, Bitcoin has some fancy systems out for block propagation, but the peer-to-peer, understanding the peer-to-peer system is relatively simple. And you don't have, as long as you have enough connections across a sparse network, broadcasting blocks is fine, and the number of miners has nothing to do with the peer-to-peer network complexity. In BFT consensus, this is different because everyone who is part of consensus has to vote on each block. So in proof of work, one miner makes each block, and most of the miners do nothing, right? Maybe they help gossip stuff because they're nice. But in BFT consensus, every validator must vote on each block. This means that you have, in general, you have something like n-squared message complexity, which is what Tendermint has. Think of this as each validator sends a message to each other validator. That's how you get n-squared. There, more, it could be some constant times n-squared, but that's the basic reason. The only way to improve this is to use a leader and send the messages to them. So this is a distributed systems restriction or a distributed systems constraint, and it doesn't. The constant factor can be changed by different protocols like Tendermint versus hot stuff or whatever, but the only way to make the asymptotic complexity better is to use a leader to whom you send messages, and you still have to fall back to a worst case n-squared protocol because the leader might be offline. So this is a hard constraint. And if Zcash wants to use a BFT consensus, the theoreticians at least have made your problem simpler. There is nothing you can do that will get around this. You can make the constant factor better, but you can never get rid of the asymptotic worst case. And this is the constraint that limits the number of validators. So, if we go back in history, we ended up with all these like proof of stake systems. Why did we end up with these complex proof of stake systems? Well, it's because not everyone could be a validator. And the reason not everyone could be a validator is because of this n-squared message complexity. So it all comes back to this. Now, it's worth noting that that's like the theoretical or asymptotic bound, but the constant factors can be widely different. So Tendermint's peer-to-peer system as it stands is like not very theoretically optimal. It's kind of dumb. I think the Tendermint team would probably agree with this opinion. It just takes time to implement good peer-to-peer systems. So Tendermint can only do a few hundred validators, but probably a like much more optimal implementation could handle, even a few thousand validators without problem, even with n-squared. So there are big variations in the like constant factor that are possible, but the asymptotic bound will still hold. So the way sort of proof of stake systems like Ethereum get larger numbers of validators is that they give up fast finality, which means that they have more people sending messages, but the messages are aggregated over a longer period of time. And you can, that's also an option. Maybe fast finality is not important to Zcash, but it is generally important for interoperability because you need to finalize blocks in order to send messages to other domains like other chains in ways that they can credibly believe are final and won't be reverted. So to come back to this question above, the question of can individual users participate in consensus or do they delegate to large validators? I can partially answer that at the level of BFT consensus, which is that in BFT consensus systems, there will be some restriction on the number of validators. It's going to be like some constant number, which could be, from the hundreds to the thousands, maybe even the tens of thousands, if you're willing to trade a little bit of fast finality for more validators, but it's never going to be infinite. It's never going to be the same thing as proof of work, where anyone can just join. Maybe you can like approximate it to more and more degrees as you trade more and more fast finality for more validators. But even in an Ethereum system, it's going to require like a deposit of some ZEC or something, and you must have at least 50 ZEC to be a validator. It's never going to be completely free. That has nothing to do with which proof of stake system Zcash chooses. It's just a property of the consensus. Cool. I should stop for questions here.
Anybody have a follow-up question to that? I don't see any raised hands at the moment, Chris. So, Alfredo.
Yeah, so I don't know much about proof of stake, but what is the motivation for a validator to do its work?
Right. Good question. So validators do a lot of things, and some of them in proof of stake systems, some of them are maybe explicitly incentivized and others of them are not. This is also true in proof of work systems. So in proof of work systems, most miners also broadcast blocks on not only their own blocks, but they also like relay messages on the peer-to-peer network, and full nodes relay messages on the peer-to-peer network. There's not really any reason for them to do that other than like altruism, right? And some hope that, they'll be tit for tat if other people do it. So proof of stake systems have a similar kind of split where some of the things the validators do, like voting on blocks, generally is explicitly incentivized because it's like critical and you could detect it. But relaying messages on the peer-to-peer network is very hard to detect in a sort of systemically accurate way. And it's something that validators seem to be altruistic enough to mostly do anyways, so there aren't explicit incentives for it. So usually in proof of stake systems, there are incentives for validators to produce blocks and to sign blocks. In proof of work systems, there's an incentive for miners to produce blocks, and no one else needs to sign them. In proof of stake systems, the proposer needs to produce a block, and other validators need to sign it. And in general, there are incentives for both of those things. Cool.
Yeah. No more raised hands, so we can continue.
Okay. So I wanted to address this kind of second part of this question, which is delegation. Delegation in proof of stake. So delegation is basically an attempt to kind of band-aid the problem of we can't have infinite validators. So not everyone could be a validator. That sucks. We want this protocol to be permissionless. You know, we want people to be able to join. We don't want 100 validators or even fewer, or sometimes to have total control over the network. That seems bad. Also, a lot of people have the assets, and we want them to be able to participate in the rewards of proof of stake. That's often also a reason. This is why delegation was invented, as far as I understand the historical record. So delegation is kind of like a, oh, we can't have as many validators as we want because of this message complexity. So this is sort of our attempt to do the next best thing from a kind of decentralization and an equitability of rewards perspective. Delegation in proof of stake, generally for all proof of stake systems that I know of, it works basically the same way. It is at a super high level, which is that a delegator, which is someone who holds the proof of stake token, quote, lends some tokens to a validator. And those tokens, usually those tokens contribute to the validator's voting power and rewards. And the validator it's back some rewards to the delegator. Basically, all proof of stake systems have these three components. So the delegator has some tokens. In general, they lock them up or they kind of lend them to a validator in a way that's like protocol enforced. Of course, you could always just send them to the validator, but that's not the kind of proof of stake system that you need to build a protocol. People could do it anyways. Those tokens contribute to the validator's voting power, but the validator does not. Like they don't have the ability to send them, right, in these sort of protocol-based proof of stake systems. And they contribute to the validator's rewards, and then the validator pays back some rewards to the delegator. And different proof of stake systems vary in like which of these components are sort of fixed in the protocol and which of them are flexible. For example, Cosmos fixes all of them, or the Cosmos SDK proof of stake system fixes all of them. So delegators, the tokens are lent to the validator in a way which is controlled by the protocol. The rewards are distributed by the protocol, and the validator can't not give the delegator their rewards. The protocol enforces the distribution of rewards. Tezos's proof of stake system, by contrast, does not enforce reward distribution. So the validator gets the kind of benefits, and it's up to the validators, sort of instead of like market mechanism, to see how the validators choose to compensate their delegators for the tokens which they were lent. And different validators do different things, as far at least the last time I checked in that system. Yeah, so I don't know to what extent this specific distinction is important for Zcash, but just kind of this is a general characterization of the features of delegation and proof of stake systems, and how they work. So maybe, this question was, can individual users participate in consensus, or do they have to delegate to large validators? Well, delegation is it's a kind of answer to that question. Users do have to delegate. Not everyone could be a validator. Users don't have to delegate specifically to large validators. They can delegate to whomever they want, and they can change their delegation if they don't like the validator. They're almost always revocable. So there is it's kind of like a layer of representative election, if you want to think of it that way. Delegators pick the validators. The validators get the actual voting weighting consensus, but delegators can decide that they don't like their validator and they could change. So there is some feedback there, which might lead validators to do good things for the delegators, one hopes. Does that make sense?
Yeah, thank you.
Cool. Yeah, but it's important that, just to reiterate one more time, the distinction of whether or not individual users can participate in consensus, it's not a distinction that has to do with the specific proof of stake algorithm. It's a distinction that has to do only with the constraint of BFT systems. So if you adopt a BFT system for Zcash, then there will need to be some restriction on the number of validators, and some users will be unable to be validators, at least as far as the theoretical bounds go, those are kind of hard constraints. Yeah. Okay. Maybe here I'll ask where I should go. So here I can go in two directions. I can go to talking about some of the advantages of Tendermint, Cosmos SDK, proof of stake, IBC, confer what advantages they might confer on Zcash, or I can go to a little bit deeper into the different options for specific proof of stake systems. Which would people prefer?
Does anybody have a preference? Yeah, Deirdre. Deirdre, you got your hand raised. Is there a preference on?
I was muted. I'm sorry.
Oh, sorry.
Different kinds of proof of stake systems because different ways of staking can have different privacy implications. So I'm interested in that.
Right. Yes, I can do that. Okay. So kinds of proof of stake. Right. Maybe specifically with regards to privacy implications. Privacy implications. As far as I know of, just to get this out of the bat, there's maybe we should privacy and proof of stake. Let's talk about this first. Okay, so it's important to note that the proof of stake is kind of a way to give validators voting power in consensus. Privacy in proof of stake is independent to privacy in transfers. So Zcash could have a transparent proof of stake system and still have shielded transfers. Those are not like incompatible things. Or Zcash someone could have a private proof of stake system and transparent transfers, which seems weird, but they could do it. Those dimensions are independent. Is independent of privacy in transfers. Also, the validators have to be public, at least the public keys. There can be pseudonymous validators. There are pseudonymous validators actually in the Cosmos, I think. But the public keys of the validators and their voting weights have to be public because this is required to verify the blockchain. So those can't be, I mean, you could have the Genesis be public and do some kind of FHE thing where you proved every time that it was more than 2/3. I guess that's possible. So I should qualify a little bit, but it's like way out of the scope of what's possible soon. So, in the sort of relatively soon, like next few years, and no one has ever built such a system, to be clear, but it is possible in principle. But in the sort of like plausible world of proof of stake systems, the public keys and voting weights of validators are going to be public. Now, there's a question as to whether, are the delegations private? As far as I know, there are, in terms of existing proof of stake systems, there are two different answers to this question. There's the sort of Cosmos SDK answer, there's the Namada answer, and then there's the Penumbra answer. In particular, there's a connection between privacy and fungibility that is important. So whether or not you have privacy in delegations in a proof of stake system actually constrained, it's not independent of how the system works in the sense of whether delegations of different delegators are fungible. So in Penumbra's system, which, as least as I understand it, has private delegations which are fungible when to the same validator. And in the Cosmos SDK has public delegations, are fungible, and Namada has public delegations which are not fungible. And the reason here I can, I think Penumbra's system is pretty well described in their protocol spec. It's more similar to the Cosmos SDK system than Namada system. The reason in Namada system the delegations are not fungible is that it allows you to perform more precise accounting for slashing. So in particular, delegations, in some very security-wise sense aren't fungible because they were made at different times. Fungible here means modulo amount generally, but because they were made at different times and infractions happen at different times. So Namada, which at least for the moment is interested in very precise tracking of which delegators contributed to which infractions, needs for this to work delegations to be non-fungible. So we actually can't make them, at least not completely private. Penumbra doesn't, it has a sort of slightly a more approximate system of infraction accounting, which may well be fine, but it's just slightly different. And they, in accordance or sort of constraint, in accordance with that, they have private delegations. It's maybe another sort of interesting question that's related to this is one of assets. So in Zcash at the moment has one asset. In Penumbra and Namada, there are kind of multiple assets, and the assets which may be privately transferred are not necessarily the proof of stake assets. It's not a constraint, but that probably affects like user privacy in sort of meaningful ways. So if users are using, for example, in a world like what Zcash could decide that there are going to be two assets. There's going to be like the Zcash proof of stake asset, and there's going to be the Zcash transfer asset. Maybe this is unlikely, but it's at least possible. But in this world, when users are delegating, they're definitely not leaking any information about their transactions because it's a different asset. Whereas in a world where those are the same asset, then potentially a public proof of stake system is more of a concern because people would have to unshield always to like delegate or whatever. So I think that's an interesting point to note.
Alfredo? I think you're muted. Oh, yeah, we can't hear you. Yeah, I think something happened. Maybe if you want to type your question in the chat, I can relay it. But yeah, okay. Yeah, I think we can continue, Chris, because I'll wait to see if that question comes through.
Okay. Did that answer the question on proof of stake privacy, or there are other aspects there that would be helpful to cover?
I think that made it clear, at least to me. Alfredo wants to mention that. Yeah, so in Kedit is developing Zcash shielded assets. So maybe if we could, there will be a future, even if it's not a transfer asset, Zach, and a proof of stake asset. We would have these other shielded assets in the protocol.
Mm-hmm.
So would that, does that affect this kind of what you've touched on there, like shielded assets? Like if there's shielded assets on Zcash, this all, you obviously won't be delegating those as the staking token.
I mean, so their privacy can mean there are like different ways to measure privacy, right? One way to measure privacy is or that we might care about is the like total size of the shielded pool. Whether or not whether tokens are in proof of stake or not. I think actually you might always have to know this, at least not without FHE. But still, you could have like transfer or amount privacy so that when users delegate, it's not like they don't reveal the amount that they moved or whatever. Maybe another useful thing to note, so if Zcash has like Zcash shielded assets, let's just assume that there's some assets on Zcash that are not used for proof of stake, right? Then the only difference that a transparent or private proof of stake system makes to the privacy of those assets is that it like changes the size of the shielded pool somewhat. But there's no risk of linkage for those assets which are not used in proof of stake. Whereas if there's an asset which is used in proof of stake, in sort of a like, maybe if you are very careful, it wouldn't be a problem, but an easy mistake for a user to make, since there is potentially some linkage when you're moving to and from the proof of stake system, and that requires that shielding.
Okay.
You ask, do all proof of stake systems have this delegation thing? I have some concern about about 2 or 3 big proxies having all the weight. There are proof of stake system. I mean, there are proof of stake systems with more validators. You can have a proof of stake system without delegation, but there's still a constraint on the number of validators. Then you would just have like more validators, and no one who wasn't a validator would have any power at all. Delegation at least gives them some power. At least that's usually the rationale. The incentives do vary. So the Cosmos system, all of these proof of stake systems also implement slashing, which is a way to punish validators for misbehaving. Namada specifically implements something called cubic slashing, which is a way to punish validators for correlated faults, meaning that if a large validator commits a fault, or if several small validators commit a fault at the same time, but that indicates that they might be controlled by the same party, then they get punished more. So there are ways to create incentives which kind of like discourage validator centralization to some degree. These are it's not like a protocol constraint. You can't, because the validators aren't Sybil resistant, they're just public keys. There's nothing you can do in the protocol to say like no validator can be more than 2%, because then Polychain or whomever will just make like multiple validators. So there are some limits on what you could do without Sybil resistance, but there are at least some incentive tweaks available in proof of stake incentive systems to try and discourage very large validators. Does that answer your question?
Yep.
Okay. Okay, kinds of proof of stake systems. So beyond actually the question of privacy, these systems are, I think, they're pretty similar. So there's like a delegation action where you delegate to a validator, an undelegation action where you undelegate to a validator, and a redelegation action where you move your tokens from one validator to another. And the reason that there's a special action for redelegation is that generally these systems have a lockup period, such that when you delegate tokens, they are locked. In the Cosmos Hub, it's for about 3 weeks, 21 days. The reason these systems have a lockup period is that in order to make the threat of slashing credible, you need to have a lockup period. So proof of stake systems are subject to they're always subject to what's known as long-range tax, which means that, I think Vitalik from a long time ago has a good blog post on this, but if there are validators who hold old keys for an old state of the proof of stake system, like a state from 5 months ago or something, but they still have the keys, and then they talk to some client who hasn't read the blockchain in 5 months, they can lie, as in they can double sign a block and they can't be punished by the protocol anymore. So there's kind of like clients of proof of stake systems need to sync at least as frequently as the unbonding period or lockup period in order to be safe under the incentive system of slashing. I don't want to go into all of the like technical nuance here. Maybe I should refer you to the blog post, but I think that's a relevant point to note, just at a high level. But yeah, so all of these systems have delegation, undelegation, redelegation, and usually they have some form of reward distribution. So validators get rewards for proposing blocks and for signing blocks that other validators proposed. And the Cosmos SDK and Namada, at least, and I presume Penumbra does, although I have to admit I don't remember, but implement a reward distribution system that's designed to like automatically pay these out to delegators pro rata with regards to the amounts of their delegations, such that if I delegate 10 tokens to a validator and you delegate 5, and the validator delegates 5 themselves, the validator will get, proportionally 5 units of rewards. You will get 5 and I will get 10. Basically, that's how the systems work. And the reason they're kind of intricate is that they have to do sort of lazy accounting in order to remain efficient in a blockchain context. But the basic thing they're doing is just implementing this proportional payout, and then they're subject to the constraint that we don't actually want to iterate over all of the delegators each block, because that would be ON in the number of delegations, which is going to be very large. So we need to do some lazy accounting for this. There's a paper on F1 fee distribution which explains this very clearly, and there's a good page of the Namada specs. I can link them if there's a way for me to provide links after this call or something.
Yeah, absolutely. And then I can include it in the recording when we post.
Right. Yeah. Okay. maybe that. Yeah, I mean, there are like a lot of implementation details of these proof of stake systems, and some of them are slightly different. But they all have the concept of bonds, which is when someone delegates to a validator, and they all have some kind of reward distribution. There are differences in privacy, and there are differences in kind of the specific slashing algorithms and what incentives they use. What do people think? Is that a good sense? Should I go into some other specific question? Go over some advantages? What would be helpful?
Yeah, that was helpful for me and very clear. I don't see any hands raised at the moment. Yeah, maybe you could go into, the specific example of Namada proof of stake, and because you mentioned that it's Tendermint and IBC only and not the Cosmos SDK, and you sort of hinted at that sort of is what makes sense for Zcash. So you could touch on that, and then we have been going for about an hour or so, but eventually I'd love for you to just do an overview of the proposal and idea you put forward on the Zcash community forum about the Zcash Namada bridge that uses Frost. We have some of the Frost engineers on the call, and I think that would be quite interesting as well.
Right. Okay. Yeah, I can do that. Yeah. So for Namada, I guess one maybe note is that the details of which proof of stake system you pick are, at least in principle, independent of whether you use the Cosmos SDK or not. The Cosmos SDK does implement a specific proof of stake system, and if you use the Cosmos SDK, you can use that system. If you don't use the Cosmos SDK, you can't. But if you use the Cosmos SDK, you don't have to use that system. So it is independent. Yeah, question?
This is a random possible aside, given that Dan reminded us that we like things, we work on threshold signing things like Frost. We can do communication for the signing in a nicely unencumbered way in terms of how we communicate. But say we wanted to do some sort of distributed key gen on a communications backbone, and it does require a broadcast channel, not just general broadcast, but it needs authentication, and it needs general guarantees of all messages being received, and we can implement that protocol. Is there anything by moving to this ecosystem that might help us in that regard, as opposed to having to implement it all from scratch, which we're kind of doing over in our little corner right now with a toy?
Yeah, so Tendermint does implement an authenticated transport.
Nice.
It's hand rolled. So
a lot of this stuff is hand rolled. I mean,
right. But they're not like, I don't know of any known bugs. I actually have a specific paper to recommend. So we've tried to do this thing, at least distributed key generation, as part of the Anoma stack in a project called Fairvio, which tries to implement distributed key generation and threshold decryption. And we design our distributed key generation system to work with Tendermint.
Nice.
So it relies upon a feature of Tendermint called vote extensions, which is in this ABCI2 upgrade, which got sadly delayed. So we've kind of had to pause our implementation. Fairvio is like on GitHub, and it sort of works in a prototype way, but it can't yet be deployed until Tendermint finalizes ABCI2. But we were doing, I think, most of what you mentioned in terms of needing an authenticated transport and sending around stuff during a DKG.
What is the best query to find that paper?
I will in some way link it afterwards, but the name is Fairvio, Ferveo, and the paper is on ICR.
Got it. Thank you.
Yeah, I mean, I will caveat this with, like, if what you want is an efficient DKG, the Tendermint peer-to-peer layer is like not really going to get you there. It's going to get you to a working one, and maybe the validator constraint is more of a constraint anyways, so it doesn't matter so much. But it's not the most efficient thing on the planet. But I think architecturally it should work. Also, that inspired me to note one of the ways that people are trying to scale the number of validators in BFT consensus systems, often with proof of stake, is by using threshold signing or signature aggregation. So I think the Ethereum community is pursuing some BLS signature aggregation stuff. Would be great if Tendermint supported this at some future point too. But even something like conceivably Frost could be used to, have what looks to Tendermint like one validator be in fact multiple key shares or something like this. And I don't know to get that to work, and if you want it to be sort of enforced by the protocol as opposed to just a decision made by a particular validator, then it might require some efforts, which I haven't thought through. But it is definitely like that kind of cryptographic work is very relevant to scaling the number of validators. So it might be an interesting angle to investigate.
Awesome.
Yeah. So yeah, Namada proof of stake. Namada proof of stake is implemented in Rust. I'll send you a link to the specs afterwards. It implements what we call cubic proof of stake. So in cubic proof of stake, it has delegation, undelegation, redelegation, all the basics, has automatic reward distribution. Namada proof of stake has automatic reward compounding, which means that rewards get automatically delegated, or so to speak. In a Cosmos-based system or Cosmos SDK-based system, you have to withdraw them and redelegate them, which works, but it creates extra transaction noise that seems unnecessary. And you can do some different things in the kind of mathematical design to make them automatically be redelegated. And in particular, Namada proof of stake implements something called cubic slashing, hence the name cubic proof of stake. Cubic slashing, I think, is interesting because it's one of the very few credible ways, at least that I'm aware of in the incentive design space, to try and discourage large validators. And the way it does that is that it punishes large validators more. So you can think of the basic thing slashing does is that when there's some kind of detect fault, validator double signed a block or they failed to sign or something, the validator gets punished, which means that some of their stake gets burned usually. You may want to, that proof of stake systems generally operate with very flexible token economics, as in like the protocol is capable of both minting and burning the native token in protocol controlled ways. I think in principle, it's possible to adapt all of this to like work with something like the Zcash sustainability fund. For this particular thing, you need the ability to burn tokens. So you should think about like, you could also send them to a community grants fund or something. The incentive should mostly work the same way. But when there's a fault, we know in general what % of voting power committed a fault. Slashing is kind of this paradoxical thing, actually, in proof of stake systems, that when you think about it for 10 seconds makes sense, and then when you think about it for like 10 minutes, it's very strange because it so happens that the only infractions that we can punish in proof of stake systems are only the ones that don't matter. So let me explain what I mean by that. So in a BFT consensus, again, remember that the system is secure and live as long as less than 1/3 of validators by voting power are Byzantine. Also, if less than 1/3 of voting powers by validator are Byzantine, if any validators commit some kind of fault, they double sign a block, or they fail to sign after a while, however you define false, sign an invalid block, then they can be identified because we have their signature and they can be punished, their stake can be burned. However, if more than 1/3 of validators commit a fault, we can still identify them. We still have their signature, but those validators, one presumes, would censor the transactions which punish them, or they would censor the evidence which might cause them to be slashed. So it's sort of this paradoxical thing where either the system is not in any kind of risk at all because less than 1/3 have committed an infraction, or more than 1/3 have, and it seems like we couldn't slash them anyway. So what gives? Sometimes I think this paradox is not clearly explained by people building proof of stake systems, and it's like slightly disingenuous. So I think they should explain it better. But I think there still is a reason that you want to do this in proof of stake designs, which is that slashing gives a very good incentive for validators to make their setup secure. So if you're operating in the world where validators are, where we're worried about malicious validators, slashing doesn't necessarily, like if there's more than 1/3 of validators who are colluding, they're going to do whatever they want. Slashing doesn't really, at least you can identify the fault. That's good. There's some social consensus backup as always. But what slashing does help with is that it gives validators a reason to make sure that it's very hard for like hackers to get into their infrastructure, or very hard for, people to DOS their nose or whatever. And that incentive seems to be useful in practice. Like validators are very careful because they get punished if they do the wrong thing. So that's kind of the at least as I understand it, the theory behind slashing incentives in proof of stake systems. Namada features cubic slashing, which basically punishes more the more percent of voting power committed a fault within the same time frame, which we hope at least will be a way to discourage very large validators and delegations to very large validators because they're more risky. So to some extent, it's a way to price in the risk to the network of having a centralized stake distribution. But that system has yet to be tested in practice. So it's still kind of experimental. There are not very many options for proof of stake incentive design. This is like the best thing, at least I personally have seen. The reason there aren't very many options is that you don't have civil resistance. Yeah, okay, Namada Zcash bridge. I realize I'm running slightly short on time. Zcash bridge. So this is independent, to be clear, to the question of Zcash proof of stake. Well, if Zcash supports proof of stake and Tendermint, then we don't need this, actually. Right. So that would be great. There's still a separate interesting question. Zcash supports, Tendermint and IBC, then Zcash can connect to any blockchain which supports IBC, including Namada and Penumbra and the Cosmos Hub and many, many, many dozen different blockchains, which would be great, I think. This Namada Zcash bridge proposal, which I'll post a link to afterwards, is a proposal to kind of bridge Zcash in Namada and through Namada, the IBC ecosystem, Cosmos ecosystem, before Zcash supports proof of stake in IBC. And whether or not it makes sense depends entirely on what Zcash's timeline is. So if Zcash plans to switch to proof of stake in 6 months, then there's no point. There's still a separate interesting question of private bridges, which is alluded to a few times in this bridge proposal post, but it is sort of orthogonal of IBC and whether or not Zcash supports it mostly. So I think there's like an interesting long-term research question into how do you make bridges private. But that is not the meat of this proposal. The meat of this proposal is a way for Zcash to be bridged to IBC before it supports proof of stake and Tendermint. And the way this works is it's kind of dumb, but it tries to preserve as much security as possible, which is that Namada validators, so Namada has a bunch of validators, right? And in this bridge proposal, Namada validators run Zcash full nodes. And then Namada validators run a big Frost multisig. And then when someone sends to, say, Zcash Namada, validators check the Zcash transaction, depositing into the multisig, and print some Zec vouchers, we can call it this. Namada, when Namada goes back, Zec goes back to Zcash from Namada validators sign a multisig transaction using Frost to release. There, validation rules involved in this, but that's basic.
Small correction, Frost is a threshold signature scheme, not to be confused with other multi-signature schemes. They are different, and they are different for reasons, and they make them differently harder to implement for reasons. So just a little correction.
Right, sorry. I will try and be careful about my words. I've become lazy in dealing with cryptography as an abstract thing, which has only information theoretic properties. Okay. Namada validators sign a threshold signature transaction using Frost. This is like IBC without IBC, as in it's the same sort of the closest you can get to the same security model as IBC. And the kind of same token transfer and voucher rules as IBC. And the way we get around needing IBC is that Namada validators run Zcash full nodes, but otherwise it's like almost the same thing. And it requires more custom implementation as opposed to using IBC, which is a nice generic reusable protocol. Yeah. So, I mean, I think Zcash should eventually use IBC. This is a temporary solution. And it would be fine, for a while. one question I have, which maybe this is a good place to ask, is how well does Frost scale?
I think that's a Deirdre or Conrado question. Yeah, Conrado, go ahead.
Yeah, we just benchmarked Frost. We ran a scenario. I think you suggested with 667 out of 1,000 signers, and in that case, it was like for each participant, each round's like under 100 milliseconds. I have no idea if that's good enough.
That's amazing. Yeah, I think that's good enough, actually, which is great. I mean, what we need to do is approximate the stake distribution, but we can approximate it to like a fixed precision, and just bound things a little bit, and it mostly works. So if we can do like on the order of 667 out of 1,000 already, it might be close enough. And if we can, one or two, a few more times that. Actually, we can do it. Could be longer than 100 milliseconds even. So if the scaling is constant, then we can multiply that by 10, and it would be definitely sufficient. And if it takes 1 second, it's fine.
That's great to know. Yeah, basically Frost, it's it's proportional to the number of signers, which we can avoid it in Frost, but I think it's fast enough to make this a specific scenario work.
And then the communication, if you already have key shares set up, you have one round of communication to commit to the things that you're going to contribute to the nonce for the signature, and then you have one round where everyone sends their share of the signature, the response. And then someone, probably one of these, validators or whoever, some party is going to just collect all those things, and that's the final bit of computation. But anyone could, in theory, having seen all those share messages go around, play that role, which is very nice. And yeah, so that is probably where the wall clock timing is really going to come from, is literally sending a round of messages and then sending another round of messages, and then you're done.
Right. Yeah, the other thing we can do is that we can pipeline this into Tendermint, so we can use the vote extensions from ABCI2 and have validators send around these signature shares when they vote.
Yeah.
And they need to send messages to each other anyway, so it doesn't change the total round complexity. It just there'll still be constant latency, more bandwidth, but yeah, it is convenient.
Cool.
Yeah, maybe the only other remark I would add here is just to describe the privacy properties. So this bridge is not private, as in Namada and Zcash at the moment. You sort of, at the moment they use incompatible circuits, but even if they use compatible circuits, it's not easy to make bridges private because you also want fault isolation. And the way you get fault isolation is by measuring the token flows. So at least naively with the ZKP only system, this is difficult to do unless you do complete recursive verification of the state machine. Then it's in a different category of thing. This bridge would allow users could send to a Zcash private or Z address on Zcash directly. They don't need to send to a T address. So in that sense, it's privacy friendly. But when you transfer over the bridge, the amount of ZEC would be revealed.
Okay. Thanks, Chris. That was very helpful. We're right on time here, so I just thank you everybody for joining, and thank you to Christopher for spending some time helping us go over all this stuff. It was really great. And yeah, if you want to share any links with me, Christopher, I can include those before I post to YouTube, and then I will also send an email to you guys as well before we post with with the link and everything.
I think we'll do.
Cool.
Thank you very much. This has been helpful.